but someone asked for the recording of it, so I am recording the screen. All right, where does the correlation coefficient come from? Well, it starts with this big, ugly formula right here. All right, which looks daunting at first. It's got a lot of stuff. It's got the summation formula, which we are somewhat familiar with, right? We know this means to add everything up. And then if we take a closer look, I'm hoping something else looks a bit familiar. This part right here. That should look familiar to everybody. Take a second. What is that? What does that look like? What does that look like? Throw in the chat, somebody. You should recognize x minus x bar. Yeah, that's a z-score right there. So this takes the z-score for the x's. And over here you see it's the same formula but for y's. And it takes the z-scores for the y's. We multiply them together. We add them up together. And then we divide it by n minus 1, where n is the number of data points. The sample size, essentially. And so to simplify this huge, ugly equation, sometimes we write it like this. 1 over n minus 1 times the sum of zx times zy. And so that makes it look a little bit more accessible. Now, what does it mean, though, to find the z's of x's and the z's of y's? All right, that's what I want to jump into a little bit more to get you a visual. So imagine we do have this data set. And a scatter plot is simply, an XY table, right? We would take all our x's and we would find the mean x bar. Then we would find the standard deviation of all those numbers. Then we would take all of our y's and find the average y value, y bar, and the standard deviation of those y values. We would then use those to do our z-score formula. So to give you sort of a picture of this, I've got an example here. So we've got a scatter plot that compares the number of wins for a baseball team versus their payroll. All right. And so here we've got our original scatter plot. And we're going to turn this into a scatter plot of z-scores. All right. And so let's pick a team right here. Let's pick a team. We're going to pick this one because I'm 99% sure I know what team that is, even though I don't follow baseball. Any baseball fans out there? You want to tell me what the team is that spends the most money? What team spends the most money? Baseball fans? No? I thought there'd be one other. The Yankees. I'm pretty sure the Yankees have had the highest payroll forever and a day. So I'm pretty sure that's the Yankees. That doesn't matter. So we take that point, that x comma y point, and we find the z-score of x, the z-score of y, and that point comes over here and becomes this one, zx comma zy. It's not my favorite thing either. All right, so we got zx and zy. We turn this point into a z-score. Now, a few other interesting things that happen with a scatter plot of z-scores. The first is where the center is, the mean. Now, we haven't really talked about centers of scatter plots, but it is there. If I look at the average payroll amount and the average number of wins, there is a point here in the middle. Now, it's not an actual team, but it's a hypothetical point of the average of x, comma, average of y. And as you can see, that's pretty close to the middle of the scatter plot. All right, at least a good representation of where the middle could be. It's not an actual team, it's a hypothetical idea. Now, what would that look like on our scatter plot of z-scores? Well, if I take x bar and find the z-score of that, well, that would be plugging it into x up here. X bar minus x bar would be 0, which is why over here, this graph is centered on 0. And if I do the same thing for y, and I plug y bar into y, the standard deviation, or it's not the standard deviation, the z-score formula for y, that becomes y bar minus y bar, which is 0. And so the x bar comma y bar point, the center, becomes 0, 0. All right? The middle is a z-score of 0. Hopefully that connects a bit to what we have done before. All right? So now that we've got all of these points turned into z-scores, what do we do with them again? Well, we take the x value and we take the y value and we multiply them. All right, well, let's think about that for a second. What are those values going to look like when we do this? So let's take our Yankees, for example, again. So if I look at those values, do you see how they are bigger than the average payroll? The x value is above the mean. How far? I don't know, a couple 100 million above the mean. But when we turn that into a z-score, it's not money anymore, it's standard deviations. So instead of being over here at 280 some million, we see that the Yankees are roughly, maybe almost 3 standard deviations above the mean, which means zx is positive. Now I'm going to do the y value. So I look over here and I see the y value is also above the mean, above y bar. Now it's up here at somewhere, maybe, I don't know if I look over, is that what, 90 wins maybe? You might call that 90 wins. But I'm not going to do wins in my scatter plot of z-scores. I'm going to do z-scores. How many standard deviations? Well, if I go up here, how far above the mean are we? That looks like maybe 1, maybe a little bit more than 1 above the mean. So that means that this y value, zy, is also positive. And again, remember we are multiplying zx times zy, and so a positive times a positive will end up with a result of a positive number. And that logic holds for all of these points. All right, the x and the y are both positive. So all of these points here are going to be positives. And by a similar logic, we can do the bottom left quadrant as well, because all of these points are below the mean in terms of payroll, and they're below the mean in terms of number of wins, and so these will be a negative z-score, comma, negative z-score. But remember, we're multiplying those two together, so a negative times a negative will actually yield another positive result. So all of these points down here are also sort of positive numbers in my calculation for R. They're all positive numbers. Now my other ones, my leftover ones, these ones here, and this one over here, those are going to give me negative numbers. Why are they going to give me negative numbers? Well, these points in the top left have a negative payroll z-score and a positive win rate. All right, so all of these points over here, these two right here, they are below the mean for payroll, but they are above the mean for number of wins. But a negative times a positive will yield a negative overall result. And then hopefully this one, you can see that will be a positive comma negative. It's above the mean on the x direction, but below the mean on the y direction. So all of these points will yield a negative result as well. So after we multiply the zx's and the zy's, we then have to add them together. So we add all the positives, we add all the negatives, and hopefully you can see that the green highlighted dots, the positive ones, will greatly outweigh the negative ones, which is why in this case, r is going to be greater than 0. All right, r is definitely going to be a big positive number. Well, less than 1 certainly, but r will definitely be positive because these positive results, which is a positive correlation, definitely outweigh the negative ones. Now, the reason why we have to multiply by this over here is if I added another point, say this one right here, well, that would be another positive number. That would just make this sum bigger. And if I kept adding points, the sum would just get bigger and bigger and bigger. Well, that doesn't mean my correlation is stronger just because I have more points. And so we had to find a way to where more points did not mean a bigger correlation. That's kind of that issue. Remember range? Some of us were tempted to say that more data meant a bigger range. No, we don't want more data to mean a bigger range. That's not quite it. And the same thing kind of goes here. We don't want more data to mean a bigger correlation. So we divide by the number of data points. All right. It kind of turns it into an average almost, but not quite really. By number of points. That way, if you have more points, that doesn't mean your correlation just gets bigger. Okay. All right. So that's kind of how that calculation goes and sort of the background to it. Now, what does that do for us? What are some other interesting characteristics? Well, first, the slope of this z-score scatter plot, the slope of the z-score scatter plot regression is actually equal to the correlation, R. If I drew the regression line through all these green dots, the slope of that line would just be R, the correlation coefficient. Kind of an interesting thing there. But we're not really interested in the slope of the z-score chart. We really want the slope of the regression line over here, don't we? That's what we're usually interested in. We don't usually do the z-score scatter plot. It exists, it's there, but kind of in the background. So how can we get over to that slope? Well, that's where this gets pretty darn complicated, but I'm going to do my best to try to talk to you about this. So one concept that I'm hoping makes some sense. If I go 1 standard deviation to the right, puts me here. If this was a perfect correlation, that would mean I would go up 1 standard deviation in the y direction. So that's about right here, puts me back right about there. And if this was a perfect correlation, if I went backwards 1 standard deviation and went down 1 standard deviation, so going down 1 standard deviation means I go down 1 standard deviation in the y. That would be a perfect correlation. Now, nothing is really perfectly correlated. And so if I were to actually draw this correlation line, it wouldn't be that steep. It would be more something like this. I'm going to exaggerate it a little bit, but it would be more like that. And so now, if I go 1 standard deviation in the x, I don't go 1 standard deviation in the y. It didn't quite go up enough. All right, we've got just a little bit of distance right here between the two. You don't quite go 1 full standard deviation up. You go a little bit less. How much less? R standard deviations less. All right, so if x increases by 1 standard deviation, then the y value increases by only r standard deviations. Remember, r is a little bit less than 1. It doesn't quite go up as much. It's not as perfectly correlated, which is why this is basically a fancy way of saying rise over run, right? If I go over 1, I only go up r when r is slightly less. So here my slope is equal to r. With the invisible 1 underneath the r, that's the x going up by 1. Now, how do I shoot that concept back over to here? All right, this is where it gets a little weird. So again, if I go over 1 standard deviation this way, plus 1 standard deviation, well, this graph isn't measured in standard deviations. So how do I convert that 1 standard deviation back into millions of dollars? Well, I have to multiply by whatever that standard deviation of x is. So when I'm looking at my rise over my run has to be the standard deviation of x. And if I'm going to go up r standard deviations in the y, all right, remember, if we increase by only r standard deviations, that's a change in y. Well, I don't want to do standard deviations. I need number of wins. So how do I turn standard deviations back into number of wins? I multiply by the standard deviation of y. But it's not just the standard deviation of y, it's r times the standard deviation of y. And we usually put the r in front. You can put it in the numerator if you want to. But there is our slope for the regression equation right there. And so the slope of that regression line that you hopefully know how to use, that's where r is inside of it. Whew. That was a lot, ladies and gentlemen. All right, that was a lot. That is a very complicated idea. If you're like, holy crap, I don't really get that much, try not to sweat it too much. Don't lose sleep over it. You aren't really going to have to need to recreate that ever. It's just background information to help you understand what the heck r is. And this equation here is important, but not yet. Give it a couple of days and we're going to come back to it, and I will try to give you more background to use and understand that equation, okay? All right, if I lost you, shake it off, shake it off, come back to me. Here are some characteristics of correlation that you do need to know. I've mentioned a few of these, I think, but if I haven't, I'm mentioning them now. Correlation has no units, okay? Correlation has no units. Because we converted everything into z-scores, there are no units here. Okay, so it doesn't matter if you're looking at miles, kilometers, feet, time, seconds. R has none of that. And one thing that does, because R has no units, it doesn't matter which variable you make the explanatory or which variable you make the response. Correlation doesn't care. So if I took this example and I switched payroll and I switched it with number of wins, and I said, you know what? I'm not going to use payroll to predict number of wins. I'm going to use number of wins to predict payroll. How high can Mr. Bolt go? The correlation would be the same. Mathematically, that's actually kind of easy to understand, Look at this multiplication problem. We're taking zx and multiplying by zy. If I flip those around, that doesn't change multiplication. Order does not matter in multiplication. So if we switch x and y, that does not change the correlation. R would be the same. It's kind of a cool thing there. Pretty easy to see algebraically, hopefully, because it's multiplication. All right? Correlation doesn't care which one is explanatory or response. There are other reasons why you have to differentiate between explanatory and response. Correlation just isn't one of those reasons. All right, and lastly, these are all kind of related. If you change your units, that also will not affect correlation. Again, units don't really matter with correlation because you turn everything into z-scores anyways. So if you have a data set and you change it from miles per hour to kilometers per hour, correlation does not change. If you go from feet to inches, correlation will not change. Oh dear. Adele, you're scaring me. Can you guys not hear me? Oh, my heart like died for a second. I'm not gonna lie. If I was just droning on for what, 20 freaking minutes and nobody said anything, I would be pissed. All right, those are definitely